Is it now visible?
Yes, sir.
Yes, sir.
Right. What we already have studied is about the basics of induction motor, right? Why do we call it as induction motor? It's a singly excited machine, right? And when we connect it to the three-phase supply, a rotating magnetic field is developed. So we already has discussed about this theory, right? And hopefully now you know something about the synchronous speed, which is being given as by the expression ns equals to 120 f by P, where F stands for frequency and P stands for number of poles, right? Hopefully, you also now familiar with the word called as slip. Are you familiar with this slip? Yes. What the slip is? It is the relative difference between the synchronous speed and the rotor speed, right? We call it as slip. I guess you are very much familiar with these two words now. Okay. And in the last class, we were started discussing about the analysis and performance of induction motor, analysis and performance of induction motor, and that too on the basis of the equivalent circuit, right? And for that, what we were using is the per phase equivalent circuit, right? Per phase equivalent circuit we have used, okay, for that. And as far as this per phase equivalent circuit of a polyphase induction motor is concerned, right? Polyphase induction motor are of two types. One, as being said by Astu, right? We can classify the three phase or polyphase induction motors into two categories. One is squirrel cage type and other as wound rotor or slip ring motor type, right? And they both are on the basis of kind of rotor being used. So as far as this per phase equivalent circuit is concerned, we know that this is the per phase equivalent circuit where this represent the stator winding having the components stator resistance and stator reactance along with the rotor side resistance and the reactance. So if this is XR dash and this is RR dash by S, that is the rotor side resistance and reactance, right? The mutual inductance being, as we know that we only excite physically, we only excite the stator winding in case of polyphase induction motor, whereas the rotor receives the energy from the stator by the means of induction. To symbolize that, we have the shunt branch and this. So this is the per phase equivalent circuit, right? We already, I guess, have discussed why do we associate this slip with the resistance, not with the reactance. Does we have discussed this fact? Yes or no? मेरी आवाज जा रही है क्लास को?
Yes, sir.
हाँ, तो क्या हमने वो डिस्कस किया है कि क्यों रेजिस्टेंस के साथ स्लिप की वैल्यू को अटैच कर दिया है? ओके, so let us discuss this first, right? This is the per phase equivalent circuit, and this circuit can further be modified to have an approximate equivalent circuit. We call it as approximate equivalent circuit, and approximate equivalent circuit will be such that we will be shifting the shunt branch towards the left, right? So we'll have a approximate equivalent circuit in which this shunt branch will be shifted to the leftmost side, whereas we'll have a resistance, a reactance of the stator side and the resistance of the rotor side. This will be the per phase equivalent circuit, that is being approximate equivalent circuit, right? Where this represents the stator resistance, stator reactance, rotor reactance referred to the stator side. This dash means referred to the other side, that is being stator side, right? And this is the rotor resistance referred to the stator side. This is XM, right? And applied voltage V is being applied over here. So the current that flows in the rotor winding will be the rotor current, and we can call it as IR dash. So from here we have derived that the rotor current IR dash that is being referred to the stator side, when being referred to the stator side, that will be equals to how much? That will be equals to V, because V is the applied voltage and I is the current that is being flowing in this branch. So how much this I will be? I will be equals to V divided by the impedance of this branch. That will be equals to Rs plus Rr dash by S plus J times of Xs plus Xr dash. Hopefully it's being clear to you. Is it clear? Is this clear, Bacho?
Yes, sir.
Right. Now, further, what we learned is कि if we see the reactance rotor side equivalent circuit, so in the rotor side equivalent circuit, what we have is the reactance and the resistance, right? Of course, your slip is being associated with the reactance, as slip is the term which is being associated with the frequency, right? Slip is what? It is just a frequency. So if we see, if we see on the rotor side, what we'll feel? We'll feel that the EMF that is being induced on the rotor, that is equals to S time of E1. So that is also being associated with the slip. Actually, it will be. Similarly, your reactance, that is X2, that will also be associated with the slip, whereas R2 will be independent to the slip, right? R doesn't varies with the frequency. We know reactance varies with the frequency, as X2 is what? It is equals to 2 pi F2 L2, and F2 is what? It is S time of F1. So we can write this X2 as 2 pi S F1 L2. That means it is equals to S time of 2 pi F1 L2, and that can be counted as reactance at slip 0, right? Or slip 1. That can be counted as reactance at slip 1 when frequency F1 is equals to F2. So this is nothing but it is S time of X0. So this is S of X0, right? But because to counter this effect on the 2, instead of getting this, what we do, and from here the current that will be flowing, if we calculate the value of current from here, that current will be equals to IR will be equals to how much? It will be S time of E2 divided by R2 plus J times of SX2. Yes or no? For this circuit, for this rotor equivalent circuit, this is the rotor equivalent circuit. Is this clear, bacho? So this will be this. But if by taking this S common, we can write this as E2 divided by R2 by S plus J times of X2. So we use this formulation instead of this one, and this says that instead of this SE2 we will write E2, then there will be a current flow. If we take IR, that will be equals to this one. This IR will be same if we instead of this consider this circuit also, right? So this will be IR into X2 into R2 by S. So this is the equivalent circuit for the rotor, right? So this is the rotor equivalent circuit. Now in this rotor circuit, equivalent circuit, the power that is being received by this rotor equivalent circuit, we call it as air gap power. We call it as air gap power. Air gap power that is being received by the rotor circuit from the air gap, through the air gap basically, right? And the expression for this is 3 times of IR dash square into RR dash by S. This will be the air gap power, right? Hopefully we discussed that this is the total amount of power which is being received by the rotor circuit, right? Now what will happen there, if we exclude the losses of the rotor circuit from this total power, we'll get the power that will be available to us as the mechanical power, right? So if we, what I'm saying is, to get the mechanical power developed by the motor, let it be PM, mechanical power, that will be equals to the air gap power minus losses of the core, minus losses on the rotor side, right? Now if we talk about losses, there are two dominant losses, one called as the copper loss and other called as the core loss, right? But what happens is when your motor is running at a full speed, that means it will be running near to the synchronous speed. Yes or no? फुल स्पीड का मतलब यह है कि वो सिंक्रोनस स्पीड के आसपास रन कर रही होगी. Yes or no? अरे बोलिए भाई,
Yes, sir.
Yes, sir.
है ना? अगर वो फुल स्पीड पे चल रही है, इसका मतलब कहीं ना कहीं सिंक्रोनस स्पीड के आसपास चल रही है। यदि वो सिंक्रोनस स्पीड के आसपास चल रही है, इसका मतलब जो रोटर फ्रीक्वेंसी है, रोटर साइड जो फ्रीक्वेंसी है E2 की या I2 की, इट इज इक्वल टू एस टाइम ऑफ F1। तो अगर ये स्लिप की वैल्यू बहुत कम है तो F2 की वैल्यू भी बहुत कम होगी। यस और नो?
Yes, sir.
So F2 is small, F2 is very very small, right? Very very small. When your motor rotates, when motor rotates or rotor rotates with full speed, right? Now in that case, what happens? Once your frequency is very low, so frequency dependent losses, they becomes very low, right? Becomes very low, क्योंकि फ्रीक्वेंसी कम हो गई तो फ्रीक्वेंसी डिपेंडेंट लॉसेस भी क्या होंगे? कम हो जाएंगे, राइट? नाउ व्हाट आर दी फ्रीक्वेंसी डिपेंडेंट लॉसेस? Basically core losses are the frequency dependent losses, right? So that's why what we do, we exclude these core losses from this losses and we only consider the copper loss, right? सर मैं क्लास में हूं, अभी थोड़ी देर बाद बात करूंगा जी। नहीं चलेगा सर, नहीं चलेगा ना। अगर दिल्ली से 12th है तो कैटेगरी सर्टिफिकेट भी दिल्ली का ही चाहिए। उसको आप मतलब रेज कर दो क्वेरी कि भाई तुम्हारा सर्टिफिकेट बाहर का है, उसके बाद कैंसिल कर देना, रीजन बदलना ही पड़ेगा उसका। है सर? हाँ वो तो है सर, वो तो है, लेकिन इसे भी लिख दो कि ये बनवा देगा, है ना? ठीक ठीक है सर, मैं जरा क्लास में था, मैं क्लास कर लूँ एक बार, है? ठीक 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 ठीक, है ना? So basically that's why what we do, because core losses are very low and they are dependent upon, because they are dependent upon frequency, and frequency is very very low when your motor rotates with the full speed. That's why what we do, we exclude these core losses and we only consider the copper losses, right? So that's why to get this mechanical power we can write this as, if we subtract the copper losses from the air gap power that is being received, we'll get the mechanical power, right? And of course, the copper losses that will be occurring in the rotor with the resistance of RR dash will be equals to, PCU will be equals to, if we talk about the three phase, in a one phase it will be IR square into RR dash, whereas for the three phase it will be 3 times this. So mechanical power will be equals to this PG minus of PCU, and that will be equals to how much? That will be, there will be 3 times of IR dash square into RR dash 1 minus S over S, right? So this will be the mechanical power that will be developed. We also know that for calculating the torque to be developed by the motor, we know that the torque is nothing but it is the ratio of power to the angular speed, right? So Pm divided by omega m gives us the torque that will be developed by the motor, right, on the shaft. That is the shaft torque, right? Now this Pm is nothing but mechanical power is Pg minus 1 minus S, Pg into 1 minus S, whereas omega m is nothing but it is omega S 1 minus S, right? If we cancel out these two, what we'll get? We'll get that T is also equals to Pg by omega S. It's the ratio of the air gap power to the synchronous speed, है ना? Angular synchronous speed. Fine. We know this Pg. This has expression of Pg is how much? It is 3 times of IR dash square into RR dash by S. So if we divide it by omega S, we'll have the expression for the torque, right? Finally, putting this value of IR dash, substituting the value of IR dash from this circuit, we'll have the final expression for the torque, that will be equals to 3 times of omega s. If we put the IR dash square values, then it will be V square over RS plus RR dash by S ka square plus XS plus XR dash ka square into RR dash by S. This will be the final expression for the torque, right? Do you agree with this? This will be the
Yes,
final
sir.
expression, right? And if we plot a characteristic in between this torque and the slip on the basis of this equation, what we'll get is the characteristic like this way. If we want to have a torque speed characteristic, right, for the induction motor, torque slip kya lo ya speed kya lo. If slip is being 0 over here and 1 over here, that means slip is 1 means NR is 0, whereas slip 0 means NR is equals to NS, right? So if we see this characteristic, how will it look like? It will be like this way. We will have a characteristic like this, right? Where this we call as, because at this moment your motor will be in starting state. So we call it as starting torque. Starting torque, right? This is the point where this torque will be maximum. So we call it as maximum torque, right? The slip at which this will occur will be called as SM, and we call it as slip at which maximum torque occurs. We denote it by SM, right? Now to find the value where does it will be occurring, what we do, we differentiate this equation with respect to slip and equate it to 0. So differentiating the torque expression with respect to slip and equating it to 0, will get an expression that slip at which maximum torque will occur, the value of the slip, right? It will be equals to plus minus of RR dash under root of RS square plus XS plus XR dash ka square, right? This will be the value of slip. And what does it states? It states that, or it identifies that this slip at which maximum torque occurs, it directly depends upon the rotor resistance, right? So if we increase the rotor resistance, that means the value at which this maximum torque is occurring, it is going to increase, right? If we increase the rotor resistance, the value is going to increase. But let us examine whether the value of the maximum torque will also occur. One thing is very clear: if we increase the rotor resistance, that means the slip at which maximum torque is occurring, it will also going to increase. Slip increases from this in this direction, right? So with the increase in rotor resistance, your slip will increase, right? Slip at which maximum torque will occur, it will increase. But whether the maximum torque will increase, so the value, if we substitute this value in the expression of the torque, we'll get the maximum value torque, right? As it will be 3 by 2 omega n s, and it will be V square over RS plus minus, it will be RS plus minus RS under root of RS square plus XS plus XR dash ka square. This will be this much, right? This will be this much. And this expression shows that your maximum torque, it does not depends upon the rotor resistance. You can see that expression is free from the rotor resistance. So what you can conclude is कि if we increase the resistance of the motor, right? If we increase the rotor resistance of the motor, what is going to change will be, right? If we going to increase the rotor resistance, what will we going to have a change? Change is will be like this: कि if we are increasing the rotor resistance, then your characteristic will shift like this way. Your characteristic will have a shift like this way, right? What does this shows? This shows that R2, green color is R2, and R2 is greater than R1, that is of red color, right? And what does it saying? That it is saying that value at which maximum torque is occurring, right? Let it be SM2, right? It is being higher because of higher rotor resistance, right? But the maximum torque values, see the maximum torque values for the both cases, they both are similar, right? So maximum torque value is not going to change. It will be constant. If you increase the rotor resistance, maximum torque will be constant, right? But the slip at which maximum torque will be occurring, it is going to change with respect to the change in rotor resistance. Also, there will be a change in the starting torque. So in case we have a motor, we have a slip ring motor, but the torque that is being generated by that motor is not sufficient enough to start the load. What we can do is we can add on the external resistance to it so that we can get a higher starting torque. Right? Is this clear? Is this clear?
Yes, sir.
Right. So
Yes,
that
sir.
was all about the basics of the induction motor, and hopefully you have understood the concept. Let us start discussing about the starters for the induction motor. Starters. Right. Although the machine is right, although we know that this machine is self-starting or not, although polyphase induction motor is self-starting or not,
Yes, sir.
although polyphase induction motor is self-starting, right, is self-starting. What does it mean? It means कि if we buy a three-phase induction motor and we directly plug it onto a supply, it will start rotating, right? That means we can start it direct online. And in fact, your smaller rating machines, right, smaller rating machines are being started with the direct online starting, right? We call it as direct online starting, right? But with the higher rating machines, but right, this is for lower rating machines. But in case of higher rating machines, in case of higher rating machines, what happens? The starting current is very high. Starting current is high, right? Starting current is very high. That is around 5 to 7 times of the, right? 5 to is very high, is very high. That is around 5 to 7 times of the full load current, right, of rated current, right? So to basically to keep this in a, to keep this current, starting current in a permissible limit, we use starters, right? Now what happens, where the motor load inertia, right, in the drives where motor load inertia is not too high, this transient of being starting, this transient state of starting, it gets completed within the shorter time period, right? So it doesn't being raised the temperature of the motor to a certainly at a high level. But in those drives where the motor load inertia is too much high, what happens, this transient state of starting, it took a quite larger time, and in that larger time, what happens, the your temperature of the motor, it may rise because of the high starting current it is being taken, right, during that starting. So to limit that is high starting current so that your motor can be protected from overheating, right, and the damage, starters are being used. So I guess it's being clear to the class कि we do not use starters to start the induction motor, but is to the basic purpose is to limit the starting current, right? Is this clear बच्चों? अरे हाँ
Yes,
ना तो
sir.
बोल दो.
Yes, sir.
We have different type of starters, but mainly the types of starters that are being used are, they are the following types of starters. One is the star delta starter, and this is the very common and very popular starter for induction motor is the star delta starter. We can also use auto transformers to start the or to limit the starting current basically, right? There is the reactor starters. In place of auto transformer, you can use the reactor starters, right? We can also use the part winding starter or AC voltage controller or saturable reactor. But apart from that, rotor resistance starter is also used for wound rotor, right? We can also use rotor resistance starter for wound rotor machine. It's very easy to understand all kind of starting methods, but the most popular is the star delta, and I will explain this only to you, right? What happens in this? Obviously, you could be knowing. Have you ever learned about this star delta transformer? Hmm? स्टार डेल्टा स्टार्टर के बारे में पढ़ा है पहले? अरे हाँ ना तो बोल दीजिए. Have you ever learned about this star delta starter or not? Huh? My voice is going to you, up to you or not?
सर पढ़ा है.
पढ़ा है, राइट. तो क्या पढ़ा है इसके बारे में? इन दिस मेथड व्हाट वी हैव?
सर कनेक्शन को स्विच कर देते हैं जिससे कि करंट
राइट,
ज्यादा इंक्रीज नहीं होता.
वेरी गुड वेरी गुड. तो किस किस कनेक्शन को किस तरह से करते हैं इसमें? जनरली इन दिस मेथड एज बीइंग सेड बाय, कौन बोल रहा था? इन दिस मेथड एन इंडक्शन मोटर that is being designed to normally induction motor designed to normally operate in delta connection, right? जो मोटर डेल्टा कनेक्शन में चलने के लिए बनाई है नॉर्मली, राइट, इज कनेक्टेड इन स्टार. व्हाट वी डू, वी कनेक्टेड इन star during starting. Let us understand this statement. What they are saying is कि the motor which normally being be connected in delta will be connected in star during the starting. Now how will this help to us, right? We know that in case of star we have relationship between the line voltage and the phase voltage as equals to, line voltage is equals to root 3 times of phase voltage. Am I right? In case of star, your line voltage is root 3 times of phase voltage. Yes or no?
Yes sir.
So that means the phase voltage that will be applied will be root 3 times VL by root 3, right? Whereas in case of delta, your VL will be equals to VPH. So you can see over here, how will this connection, interconnection will help to us? It will be helping us by reducing the applied voltage, applied phase voltage by root 3 times when we connect the winding in star. So what we do, we first connect the windings of the motor in star, and as gradually the speed will increase and your current will come down, will finally shift it towards the delta, right? Let us see the configuration of this star delta. Okay, how can we make this connection for that? Okay, suppose these are the 3-phase lines and giving the 3-phase supply, right? We are having a 3-phase supply. Now what we are doing, we are tapping the 3 connections from here to feed the induction motor, right? Suppose we have used our MCB, 3-pole MCB, to connect or disconnect these switches, right? To connect or disconnect. Let it be CBM. It's a common one. Now we have the stator winding. Let the black color represent the stator winding, and this is the one, this is the second phase, and this is for the third phase, right? Like this way we are having the 3 windings. Okay, your this winding is be connected to this A, let it be A, right? Let it be B, and let this be C. Right? Now, we want to have an arrangement such that we can switch on these connections. We can make this as a star and delta. We know that if we connect these all these three, right, this will be A dash, this will be B dash, this will be C dash. If we connect A dash, B dash and C dash to a common point, it will become a star. Yeah, your stator winding will be in star. I guess it is very clear to you, right? So what we'll do, we'll make an arrangement to connect them in star by having the wires connecting in such a way that there will have a switch, right? We'll have a switch, one switch for this phase, right? Similarly, we'll take on the second one, right? We'll put a one line, and again the switch. Let this switch is being interconnected, right? And for the third case, this line is being connected to this one. And for the third case, we have the third line. Again a switch that is being here. एक स्विच ये था, एक स्विच ये था, ये दो ओपन पॉइंट्स हैं. तो आप देख सकते हैं यदि मैं इस स्विच को, है ना, अगर मैं ऊपर की तरफ पुश करूं तो these will be shorted, right? These three will be shorted and your winding will be then in star or delta. If I use this switch, that is, let us give us this name as the CB1. If I push this CB1 up, what will happen? Your A dash, B dash and C dash, they will be connected to a common point. Yes or no?
Yes, sir.
So if they will be connected to a common point, that means your this winding will be in star. So initially we'll push this one to start this motor, but we don't want to run it. We don't want to run this motor with this connection only because of the lower voltage applied, right? So what we want is, once your motor is being started, we need a second arrangement where we can what we can do is, where we can make this as delta connected. When it will be delta connected, we know that delta connection means to us is this the delta connection. And in the delta connection, we know that if this is A, this is A dash, then this A dash is being connected to the second coil B, right? Second coil B, it is being connected to the B end of the second coil, right? Whereas this B dash end of the second coil is being connected to the C end of the third coil. Similarly, C dash is being connected to the A, and we feed or take on the supplies from these interconnected things, right? So keeping this in mind, we know now this is the connection of the A dash. So A dash must be connected to which one? A dash must be connected to, बताइए कहां कनेक्ट होना चाहिए A dash को? अरे बोलो, this point A dash must be connected to, है क्लास में कोई या वैसे ही चल रहा है सर?
B पे.
B. So B कहाँ है? B यहाँ है. So we'll be taking this to the B, right? We'll put a one switch over here, which once can be pushed, will connect this A dash to B, right? Similarly, this is B dash. B dash must be connected to C, right? So we'll pass on it to C. This is C, right? Similarly, C dash must be connected to A. Yes or no?
Yes, sir.
So C dash must be connected to A. So this is C dash. This must be connected to A. So having this switch closed, so what we do, we have three switches, CBM, CB1, CB2. Initially, to start the motor, this CBM is closed. After that, this CB2 is kept open, whereas this CB1 is being closed, so that your motor can start in star connection, right? Once your motor achieves a speed of around 70% of the final speed, this CB2, it is get opened and CB2 is being closed. CB1 is opened, whereas CB2 is closed, so that this winding of the stator becomes in delta connecting. Is this fine? So this is called as star delta transformer. Is this fine?
Yes, sir.
Whereas in case of auto transformer starter, if we talk about auto transformer starter, what happens is, suppose we are having a line, right? Again, the concept is same. We want to reduce the applied voltage so that your starting current can be limited within a permissible limits, right? So for that, what we do is, for the auto transformer starter, auto transformer is being used, right? Suppose we are having this as the motor. Your stator of the motor is being connected to this side, right? With these three switches being used, right? By push and pull, for the push and pull, right? We have, suppose, a star connected. Suppose we are having a star connected motor, and where these are the three connections, right? Is the stator of your motor. What is being done in auto transformer starting for this three-phase machine is, a three-phase auto transformer is being selected of proper rating, where we again use the three-pole switch or MCB, right, to connect or disconnect it from the supply. So this is CBM, and let it be CBS1 they have mentioned, right? So what we do, we have one three-phase auto transformer. Of course, you may be remembering that auto transformer is a kind of transformer in which we have the single winding only, right? That serve the purpose of both secondary as well as primary, right? Now what we do, initially we connect the motor, we keep our arrangement to connect this motor windings with the through this auto transformer, right? This is the first phase. For the second phase, we use again as one switch, and we connect it to the second one. Whereas the third one we use, and we tape it from here, and we take it to the switch, right? And through the switch, we again connect it to the third case. So by varying this number of turns in the auto transformer, we can vary the applied voltage across this. So earlier, so during starting, what is being, this is being kept open. Instead of being supplying it from this supply directly, what we keep this open, and we supply it through the auto transformer. Once your auto transformer, once your motor, this is the motor, right? Once this motor gradually gets an increased up to 70% of the final speed, what we do, we disconnect this and we connect this, right? So this is the way in which we use the auto transformer also, right? But nowadays what happens is, instead of these conventional methods of starting, or your soft starting methods are being used. In the soft starting methods, what is being there is that they use the control rectifiers or control switches to control this applied voltage. Instead of wasting the energy by applying these resistances or reactances, what is being done? Control switch is being used to have a better efficient way of voltage regulation, right? Now let us come to the point which is a major and important point to us, is the speed control, right? Now speed control, what are the methods? If we talk about the speed control methods, we have the following main methods. One which we call as pole changing method, right? Because we already have learned that your synchronous speed of the motor, it is ns equals to 120 f by p, right? So that means we can change the synchronous speed of the motor by changing the frequency of the supply or by changing the poles of the motor, right? So pole changing means, obviously, speed and the pole are inversely proportional, right? So if we are going to have a higher pole machine, right, then definitely the speed of that motor is going to be lower one, right? So you can see it like this way: if we are having a 6-pole machine, once being fitted with the 50 hertz supply, so the synchronous speed that you will have will be equals to, how much will be the speed then? It will be 1000 rpm, I guess. Yes or no? It will be 1000 rpm. हाँ है ना? अरे बोलिए, कोई है
Yes, sir.
क्लास?
Yes, sir.
क्लास में है नहीं कोई? बिल्कुल सुस्ता गए हो, क्या चक्कर है? वहीं अगर हम इस पोल को 12 कर दें तो हाउ मच विल बी द सिंक्रोनस स्पीड? इट विल बी, if we are increasing the pole, what will happen to the speed? It will,
So 500 हो जाएगा.
yes, it will reduce, right? So by increasing the poles, we can reduce the speed. So this is the one of the way, right, that we can increase or decrease the synchronous speed and hence the rotor speed, because we know that your induction motor will never going to have the speed higher than the synchronous speed. तो अगर synchronous speed घटा दी तो रोटर स्पीड भी घट जाएगी, क्योंकि वो उसके आगे तो जा नहीं सकता, राइट? वो उससे तेज घूम नहीं सकता, उस सिंक्रोनस स्पीड जो है जिससे रोटेटिंग मैग्नेटिक फ्लक्स घूम रहा है उसके आगे नहीं घूम सकता. व्हाट अबाउट द अदर मेथड? As also being discussed that your speed is also being proportional to the frequency. So the other method is called as stator supply frequency or supply frequency control. We call it as supply frequency control. Supply frequency control, right? Again, this method is responsible for the synchronous speed control, right? So if we will be able to control the synchronous speed, that means we'll be able to control the rotor speed. The third one is stator voltage control. I will explain you what we have in the stator voltage control, right? We already have learned that torque is proportional to the voltage square, right? So if we are going to vary this voltage, obviously we are going to have the variation in the torque, and because of that we will going to have the variation in the speed, right? So this is the third method. Fourth method is the rotor resistance control. Rotor resistance control. Of course, now everybody can tell me, anybody from the class can tell this, that this method will be applicable only to which motor?
Wound motors.
Surround rotor.
This method will only be applicable to the slip ring or wound rotor induction motor, right? Slip ring or wound rotor induction motor. As we don't have any provision to add on the rotor resistance in case of squirrel cage induction motor, right? So this method will only be applicable to the wound rotor or slip ring induction motor. Similarly, the fifth one, which is also being a very popular method, is slip power recovery method. Slip power recovery method, right? And this method is also being applicable to slip ring and wound rotor machines only, right? Because what we do in this slip power recovery method, we try to use the power that is being wasted in the rotor resistances, right? So we try to recover that, and we call it a slip recovery method. I guess it is being clear to the class. These are the 5 important methods, and these are being there in your course. So
slip वाले एक बार और बताना.
स्लिप पावर रिकवरी पढ़ेंगे एक एक करके, सारा पढ़ेंगे, अभी तो बहुत डिटेल में पढ़ेंगे, ये चिंता मत कीजिए, एक एक पढ़ेंगे, ठीक है? स्लिप पावर इज एसपीजी, जो हमने पढ़ा है वो है ना, एयर गैप पावर, और जो स्लिप टाइम्स घट रही है उसमें से उसी को रिकवर करने की बात करेंगे. विल डिस्कस इट, है ना? लेट अस डिस्कस द पोल चेंजिंग मेथड फर्स्ट, ठीक है? Pole changing method. It's very interesting to see the speed control methods of induction motor. All are very, very important and very interesting. First method is pole changing method, है ना? Now you need to know this fact that We know that for a given frequency, the synchronous speed is inversely proportional to the number of poles, right? So synchronous speed and therefore the motor speed can be changed by changing the number of poles. Now you had to keep it in mind that provision of changing the number of poles has to be incorporated at the manufacturing stage, and these kind of machines are being called as the pole changing motors or multi-speed motors, right? So we had to keep it in mind that this pole changing methodology or approach, if we want to have for the speed control, this needs to be incorporated at the time of manufacturing only, right? And we generally call these kind of machines because these will be the special machines, right? So we'll call them as multi-speed motors or pole changing motors, right? Now the simple arrangement could be, how can we change that? The simple arrangement could be ki suppose we are having, what we do, we divide the stator windings in number of groups, right? Suppose now we have the two groups, we have divided the complete coils or stator windings in two groups, right? And each group is having three windings, right? Three windings, that this is winding 1, 2 and 3. This is in one group, all right? And this is being associated, let it be poles 1, 3 and 5, that generates 1, 3 and 5. This is AB, this is the one group. We are having a second group that is of 2, 4 and 6. So each group is having three coils generating a pole 2, 4 and 6, right? So one of the way is to connect them in this way. If we connect this way and if we feed the current I from here, right? So the current flow will be like this way, and from in this it will be like this way. So obviously if these will be 1, 3 and 5 will be generating the north pole, right? Then what will happen? The 2, 4 and 6, they will be generating the south pole because the direction of the current is opposite, right? So this could be seen like this way. We have the two coils. In this there is a one A and B. This is AB and this is CD. This is CD, right? So AB, in the AB we have a coil. Let me make it again. In the AB coils we have three coils, right? AB group we have three coils, and coil means two coil sides, right? For a coil they have two coil sides. This is coil side 1, this is coil side 2. Coil side, and this is coil side 1, this is coil side 2. Hopefully you remember this word coil side, right? So this is the coil side 1. If we take it 1 for this one, right? So current flow is like this way, it is being in this direction. So we'll have the third coil that will be producing the again the pole in the coil sides with the same field, and there will be the third one. Like this way we'll have the coil arrangement, right? This will be A if we take it as A, and this is B coil, right? This is B. For C and D, what we can do is C and D will be, can be placed in between these two, right? In between these two, producing the pole in opposite direction to this. As if we will flow the current that will be in opposite direction to this, then obviously the pole that will be produced by these windings will be opposite to the previous one. So you can see that if we have a flow of current in this direction, like in this way, in these coils, obviously this will be the direction of the current. So they all will be producing the pole. Let us take in the south pole, considering this to be the south pole, right? So they will be producing the south pole. Now if we want to have the north pole from these, what we can do is we can make the current flow in the opposite direction to this, right? So we'll be feeding the current from the D to C, right? This is C, this is D. So we'll be feeding the current through the D such that the current flow is in this direction, right? And if it is in this direction, If it is in this direction, then the poles produced by these will be the north poles. Right? In this way, we'll be having a 6 poles with these 6 coils. Now, what we can do is to have the 12 poles from the same winding. What we can do is we can change the interconnection. We can change the interconnection such that the current in each windings will be in same direction. Right? If you see this connection in this 2, 4, and 6, 1, 3, 5, and 2, 4, 6. In the 2, 4, and 6, the current is in from right to left, whereas in ABC it is from left to right. Right? But if we interconnect these two coil groups in such a way that, suppose, while feeding the energy, we connect them through the supply like this way. If this is the supply, we connect the B end of this coil first, right? Then the current which is being flowing will pass on through this direction, right? Now we want the current to be in same direction. Then what we can do is we can connect this A with the D of this, so that current will be in this direction now again. So you can see that in this case, what will happen if we connect this A to D, right? If we connect this A to D, right? And if we pass on the current through A, right? Through A and C, what will happen? The current in each of the coil, it will be in same direction, right? Current in the coil will be in same direction. And because of it, what will happen? That once your current will be in same direction, right? Once your current will be in same direction, there will be the same poles that will be generated by the machine. If these are the south poles, then each will be the south pole. This will also be south pole. This will also be south. Now, what happens in this case? In the interpolar region, automatically the north pole generates. Means the flux that is being generated by these coils, they find out the path from the space in between these two poles, right? So they take the path of from in between the poles. So this becomes the north poles, and because of this connection, because of the change in this connection, you can see the 6-pole machine will become a 12-pole machine, right? So in this way, by changing the interconnections, we can change the number of poles, right? And by changing the number of poles, definitely we can vary the speed of the induction motor. So this is the one of the way. But you have to keep it in mind, this arrangement needs to be made at the manufacturer level, even if it is for rearranging the connections only. Then he should provide the connections for rearrangement, right? So this is the one of the way. Now other method which we have written is the stator voltage control. The second method for the speed control is stator voltage control. Stator voltage control, right? What we have learned is that by reducing the stator voltage, speed of a high slip induction motor can be reduced by an amount which is sufficient enough for the speed control of some fan and pump drives, right? Now what is being mentioned in the book is we know that your torque, it is proportional to the voltage square. We know that, we already have derived this expression, right? This torque is proportional to voltage square. You can see torque is proportional to voltage square, right? So we know that the torque is proportional to the voltage square, whereas current is proportional to the voltage, right? So what we know, when torque is proportional to the voltage, your current I is also proportional to the voltage. Torque is proportional to the voltage square, whereas current is proportional to the voltage, right? That means if we reduce the voltage, your current is going to reduce, right? So along with the speed, so if we are going to reduce the voltage, that means your torque, that is the speed, is going to reduce along with the torque, right? So both will be reducing. That's why this stator voltage control method, it is being suitable for those applications where the torque demand decreases with the decrement in the speed, right? What I am saying is because while torque is, let me write this for you, while torque is proportional, while torque is proportional to the voltage square, or to the square to the voltage squared, current is proportional to the voltage, proportional to the voltage, to the voltage. Now say, they are saying therefore as voltage is reduced, to reduce the speed, right, for the same motor current, or motor current, motor develops lower torque, right? So that means this stator voltage control, if we are going to use this method, what we are going to have is ki with the decrement in the voltage, your speed is going to decrease, no, of course, right? But during this decrement in the voltage, the torque that will be developed by the motor, it will also going to be affected, and it is also going to be reduced. That's why this method is only suitable, or mainly suitable, for the applications like fan, right, or pump load, where these torque demands, right, if we see the pump load have a characteristic like this one, right? So basically for the pump load, TL is basically proportional to the voltage square, right? That means with the decrement in the speed, your torque demand is going to decrease. With the increment in the speed, it is going to increase. So this method of stator voltage control is being more suitable for the loads where your load demand is decreases with the speed, and that is for the pump load, right? Now how can we vary the stator voltage control? The simple way is to use the AC voltage controllers. We all have studied about AC voltage controllers, right? These are the anti parallel connected thyristors or control switches, right? If we use this in this fashion, right, if we are having a three-phase motor and we want to control the speed, we want to control the applied voltage, how can we control this? We can control it by feeding it through the AC voltage controller. Can we control the voltage of applied voltage? Yes or no? Can we control this? Yes or no? अरे बताइए भैया। चलो आज के लिए इतना ही है, नहीं तो